Just wait for a few more people to filter in. See how we're doing. Okay, good afternoon, everyone, and thank you so much for joining us for this year's Space Public Lecture. Today we're going to be discussing the fascinating moon Titan. My name is Rose. I'm the Education Officer at the Geological Society, and we've got a brilliant talk lined up for you today about this unique and incredible moon. Now, this lecture is part of our 2021 Year of Space. This year, we're directing our gaze upwards beyond the Earth to examine rocks, landscapes, and processes on other planets. We have a brilliant programme of public lectures, outreach activities, and conferences throughout the year. This includes our free public exhibition, Spacescapes, which is on in the Burlington House courtyard at the minute. It's on till the 8th of October, so if you're fascinated by space and rocks on other planets, then do make sure, if you can, you pop down to London for a visit. So on to today's lecture, we have the fantastic Dr. Ralph Lorenz, all the way from the US, at Johns Hopkins University Applied Physics Laboratory in Maryland. Ralph is going to take us on a journey of the history and geology of Titan. If you have any questions for Ralph during this talk, we have a Q&A session at the end, so please do drop your questions in the Zoom Q&A box, or if you're watching on YouTube, please just drop them in the chat there, and we will collate those and get through as many as we can at the end of the lecture. So without further ado, I will hand over to Ralph, who's going to take us on a journey to Saturn's orbit. Over to you.
All right, thanks, Rose. Good afternoon, everyone. So I will see if I can share the screen properly. I think that looks right. Since I'm on the other side of the Atlantic, I'll turn the video off while I'm going through the talk, just to make sure there are no bandwidth issues. Yeah, Geology of Titan. For those of you who haven't heard of the Applied Physics Lab, we are on the East Coast of the US. We're associated with Johns Hopkins University in Baltimore, so we're just north of Washington, DC. But APL may be a little less well known than our West Coast counterpart, JPL. APL built the New Horizons spacecraft that went past Pluto a few years ago. We built Messenger that went to Mercury. So we've been to the innermost planet and what was once the outermost planet. We built Parker Solar Probe that's flying by the sun periodically. We're just coming up on the launch of DART, an asteroid impact mission, and we're involved in many other missions besides. Dragonfly is the one that I'm most involved with here at APL, and we'll talk about that towards the end. It's useful just to set the stage with a little bit of astronomy. Titan is the second largest moon in the solar system. It's got the optically largest diameter. It's got the thickest atmosphere of any moon in the solar system. And it's a moon of Saturn. So Saturn goes around the sun once every 29.5 Earth years, which is sort of an interesting timescale, in human terms. Because basically, depending on how lucky you are, you get to go around the sun on Titan 2 or 3 times. Basically, the Titan year also sets the timescale of how long it takes to get from the Earth to Saturn, which is 10 times further from the sun than is the Earth. So it takes about a quarter of a Titan year to get from the Earth to Saturn and Titan. And so much of the story here really is paced by that. And I'll talk about that in a second. One interesting point is that Saturn and Titan's rotational axes are inclined to their orbit around the sun. So Titan and Saturn have seasons. They're of course very long seasons compared to ours. Saturn's orbit around the sun is actually not very circular. It's appreciably elliptical. So for part of the orbit, Saturn and Titan are closer to the sun and so are warmer, and part is further away. And the orientation of that elliptical axis with the tilt of Titan's equator is such that southern summer on Titan is shorter and more intense than the north, and that actually has quite dramatic geological implications. I've put on here the major spacecraft exploration events, the Voyager encounter back in 1980 was what told us most of what we knew up to the point of Cassini and Huygens' arrival, almost one Titan year later. Cassini operated, in fact, for almost half a Titan year, 13 Earth years. Very, very epic voyage of discovery. And we'll start the process kind of all over again. And that build-up is happening now, basically one Titan year after Huygens. So we'll come back to all that. A little about me. I got into this game, in the UK, learned aerospace systems engineering, and worked for the European Space Agency in the Netherlands on the early design of Huygens, and then in Canterbury did my PhD work building one of the instruments for Huygens. I then went out to the USA and started working on Hubble maps of Titan, and then planning for Cassini, and in 2006 moved to the East Coast and have been involved in a number of projects since then. If you're paying close attention, you'll notice that the word geology does not appear anywhere here on my CV. I have no formal geological training. I'm sort of bluffing this as much as I bluff Titan oceanography and Titan meteorology and Titan astrobiology. Planetary science is a very multidisciplinary field, in fact, and obviously the technology we need to discover things about other planets demands a lot of aerospace engineering. So I make no apologies for not having a formal geology training. I think even the hardcore geologists will find something interesting in what I'll discuss. You can map the Titan year into your own life milestones. When you went to school, when you got married, and all that. You can also map it to the books you've published if you happen to have published some books. And I've written about a number of topics of aerospace engineering and planetary science, and several books on Titan. The most recent book is Haynes' Owner's Workshop Manual that was just published last year, and many of the pictures that I'll be showing in the talk are actually from this book. So if you find any of this interesting, that's maybe a good next port of call. So Titan's bigger than our moon. It's bigger than the planet Mercury. It has a gravity about the same as our moon. So, if you've seen the videos of the astronauts kind of just bounding around almost in slow motion, that's how Titan is, but with an atmosphere. The atmosphere is thicker than ours. In fact, the sea level density is about 4 times that of Earth. It's mostly nitrogen, like our atmosphere, but there's no oxygen. There are no plants. There's a few percent of methane, which acts very much like water vapor does in the Earth's atmosphere. It's a greenhouse gas. It's condensable, so it forms clouds and rain and rivers and seas, in fact. And the reason it does that is because Titan is so far from the sun. Being so far from the sun, the surface temperature is very cold, at 94 Kelvin, so minus 180 Celsius basically. And at that temperature, methane, which we know as natural gas, is liquid. Ethane is also a natural gas component and is also a liquid. The sunlight at Titan's surface is about 1,000 times less than that on Earth. There's a factor of 100 due to the the Sun-Titan distance, and there's another factor of 10 because Titan's atmosphere is very hazy. Titan's day is about 2 weeks long. Titan is tidally locked to Saturn like our moon, and in fact tides are important in Titan seas. So those are the basics. And for many years, since I started getting involved in Titan, we knew very little. I mean, we had data from the Voyager encounters in 1980 and 81, and the image on the left was basically all we saw. It was very disappointing from a geological perspective because basically you couldn't see the surface at optical wavelengths. Basically, there's several optical depths of opaque haze, a sort of organic smog that is made by the action of sunlight on the methane in Titan's atmosphere. Now, if you go to longer wavelengths of light, longer than the Voyager cameras could handle, out into the near infrared, basically around 1 micron, the wavelength of your TV remote control, then the haze gets thinner and you can actually see down to the surface. And the Hubble images that came along in 1994 look like this. Titan's about 20 pixels across. And you can see there are actually some bright bits and some dark bits. And it was sort of interesting to speculate when you sort of lay these out on a map. What are they? Is the bright bit a mountain? Is it a crater? There's just not enough detail to speculate about. Except, of course, we speculated. It seemed a natural supposition that the brighter area on Titan's leading face was somehow elevated, and there were even theories advanced that maybe elevated terrain gets rained on more, and the rain would somehow wash the dark organic stuff that we thought this haze was into lower areas. So it was all speculation. Maybe even the dark areas were liquid, liquid methane and ethane. But we didn't know for sure. So the next step is to go and find out. And Cassini was a very ambitious, large, expensive, multi-billion-dollar enterprise. It was a partnership of NASA, the European Space Agency, and in fact the Italian Space Agency. The Italian Space Agency provided the 4-meter dish for Cassini's radio communication and radar systems. I mean, Cassini's the size of a bus, right? It was 5 tons at launch. It's huge. The European Space Agency provided the 350 kilogram Huygens probe, about 2.7 meters in diameter, that was carried out to Saturn and Titan by Cassini, and then was released just before Christmas 2004, flew in space independently for 3 weeks, and then hit Titan's atmosphere at 6 kilometers a second. The tortured air reached a temperature of over 2000 degrees, but it had the probe had a heat shield, then popped a parachute at Mach 1.5 at an altitude of about 150 kilometers. I mean, Titan's atmosphere is very vertically extended as well as being dense. And then for 2.25 hours, the probe descended down to the surface. And we didn't know what was going to happen then because we had no idea what the surface was. Would we splash down in a sea of liquid methane? Would we land on a solid slab of ice and just, smash the probe into pieces? Would we land in some big pile of fluffy organic dust? We just didn't know. As it turned out, the probe continued to operate quite happily after contact with the ground. And somewhat to my surprise, the little instrument that I built in Canterbury, and you can actually see it in the Science Museum in London. It's called a penetrometer. It's basically roughly the size of my finger, 14 millimeters in diameter, and it measures the force on this little titanium bolt, which is basically stuck out of the bottom of the probe. So when the probe smacked into the ground at 5 meters a second, which is basically the speed something falls off a table on Earth, this recorded a force signature. And force signature is kind of constant. If you land in, like wet clay, there's a sort of steepening curve as sand grains lock together. If you push this into dry sand, there's big spikes if you land in gravel. And what we saw was sort of more or less constant resistance, but with a sort of spike at the beginning. And we wondered, was this something like soft snow with maybe a crust on top, like creme brulee? But what we now think, having seen the pictures from the Huygens probe, and we had no right to get this picture, right? The probe could have failed, the parachute could have flopped on top of the camera. We were just lucky that things kept working and there was actually something interesting to see. This is basically a view from about knee high off the ground. So it's very, very foreshortened in the distance. But you see rocks like almost every planetary lander sees, but these rocks are probably made of ice, maybe some sort of organic material. They're not made of silicate rocks, or silicate minerals. And they're rounded, right? They're not sharp edged, and that suggests they've been tumbled basically in a stream, a flash flood, because Titan has an active hydrological cycle where methane rain falls out of the sky and basically strong summer thunderstorms, and tumbles the particles of, in this case, we think ice, such that the corners get rounded off. So just seeing this picture and some of the other pictures from the probe really gave us, instantly transformed Titan from this, fuzzy object with vague bright and dark markings into a place that's shaped by processes that are familiar to us here on Earth. So, this is really the theme of Titan geology. You sort of need to recalibrate the language. The processes are the same. The rates at which the processes occur are probably very different, because the year is long, there's much less sunlight to drive the winds, and so on. So the processes are fundamentally the same, but under different conditions. The air is denser and gravity's lower, and so on. The materials are different too. We think the dominant crustal material is water ice, but there are likely many organic compounds present as well. There might be ice with some ammonia present, or ice with methane locked in the sort of crystal lattice, what they call methane clathrates. And all these materials have different properties, and we'll come back to the mechanical aspects of those properties. One point to note, and this becomes very important for future exploration, although Titan's atmosphere is hazy, it was opaque to Voyager because it's so vertically extended, because you're looking through 150 kilometers of atmosphere. The atmosphere in a sort of meteorological visibility sense is actually very, very clear. The visibility by the meteorological definition is something like 50 kilometers. So you can see the landscape pretty well. This is a mosaic of images from the Huygens probe as it descended. The probe sort of landed in this dark area here that we think is a stream bed. There's this sort of bright highland with some river networks that we'll talk about in a little bit, and there's a couple of dark streaks off in the distance that become important as well. Now that, of course, wasn't the end of the story. It was really only the beginning. Huygens was delivered to Titan on Cassini's third flyby of Titan. Cassini was in orbit around Saturn, making an orbit once every few weeks, and would encounter Titan once every month or so. So over the initially 4 years, then 6 years, and ultimately 13 years that Cassini was operating, it made about 125 close flybys of Titan. And during each of those, we took data with a range of instruments. Sometimes it was not geologically fulfilling, right? That we would be measuring the upper atmosphere, or we'd be doing geophysics, measuring the gravity field, because of the way the instruments were accommodated on Cassini. We couldn't do everything at once, right? Sometimes you'd use the radar, sometimes you'd use the cameras, sometimes you'd do gravity, sometimes you'd do other things. So it was very much a jigsaw puzzle on which the pieces were dealt to us very, very slowly, which is an interesting challenge if you're trying to build a scientific career and publish findings. Do you jump the gun with the preliminary indications you have on the first close look, or do you wait half a year to get more results and make the findings more secure? Anyway, once you now can sort of look back and just look at the aggregate of all of Cassini's data, and we sort of have a world view that's sort of laid out in that Haynes manual. So we think Titan's interior actually has a liquid ocean, a liquid water ocean, like that of Europa or Enceladus. But the difference is that Titan's ice crust is much thicker, probably 150 kilometers thick. So it's the internal ocean is practically inaccessible. You could argue the European ocean is practically inaccessible too, but Titan's even more so. There may be some high pressure ice phases in the interior. There's debate about that. It depends what's dissolved in the ocean. Is it pure water? Is it doped with ammonia antifreeze? Is it doped with salts? We don't know. But in the deep interior, we think there is some mixture of rock, maybe with a trace of iron, maybe some rock ice mixture. But that's the big picture. The crustal material, though, we are pretty sure is water ice, with a little veneer, maybe a few hundred meters, maybe a kilometer of organic material. And when you look, at the topography of Titan, which we were able to measure with the radar on Cassini, you find it's the hypsogram. The histogram of elevations is very different from the Earth, Moon, and Mars. It's much narrower. Basically, the topographic range from the deepest pit to the highest mountain on Titan is rather small. Now, we don't know whether that's because there just hasn't been much mountain building, or the erosive processes that wear mountains down are just much more energetic, or this ice crust is not very strong, isn't able to sustain the loads. That's an interesting problem. We could have a whole talk about these graphs here. The Earth and Mars have very bimodal hypsograms, and of course it's plate tectonics that's responsible for that on the Earth. So some things to think about big picture. The reason the Moon has very extended topography is mostly the craters. The cratering event forms a steep rim, where there's often quite big jagged mountains, and there's no process to wear those down. So the Moon has basically fossil topography. It's not sort of being actively built today, whereas the Earth's topography is very much a balance of push up and wearing down. So when you take the near-infrared pictures like the ones that Hubble took, but with Cassini's camera, which of course was much closer to Titan, you can build up this global map. And what you see is there's some bright areas and dark areas, of course. Here's that leading face bright region, which has the name Xanadu. And you see that much of the equatorial region is covered in dark stuff, as we'd seen with Hubble. And it's almost like the stuff is flowing around the bright areas, and figuring out, is this a liquid thing or is it a wind-blown thing? Was the stuff of much debate early in the Cassini mission. It was only partway through Cassini, about 2007, that we started to see these dark areas up at high latitudes. These latitudes were in winter, in darkness, when Cassini arrived, and it was only towards the end of the 2000s that we were able to see them. And these are darker than the equatorial dark areas, and they have a slightly different look to them, and we'll come back to why that is. But there's clearly been a lot of interesting processes shaping Titan. You can see a couple of circular things. These are suspiciously circular features that in many cases were subsequently determined to be impact craters, but relatively few of them compared to, say, Mars or the Moon. Most of the craters that we expected to have formed on Titan have been obliterated somehow, and we'll come back to what the process is doing that might be. We have a lot of radar data on Cassini, on Titan. The Cassini radar takes images with a resolution of about 300 meters. So it's not great by terrestrial standards at all, but in most cases this is the highest resolution information we have, and we have that data over about, depends where you draw the line, 40%, 55% of Titan surface. There are a lot of areas that we haven't studied, and the areas that we did see are largely shaped by the trajectory that Cassini took as it explored the Saturn system and flew by Titan. In some cases, we influenced that process. We were able to concentrate on areas of interest, such as those dark areas near the North Pole. But in many cases, we just had to sort of take what we got. So it turns out those dark equatorial areas are basically sand covered, some sort of organic sand, we think. And the revelation of this was basically in October 2005. On the left is a Cassini radar image, about 200 kilometers from top to bottom. And you can see basically these long ridges. And the reason we know they're ridges is because the radar was shining its radio energy from the top of the image, and the surfaces closest to the radar are bright, and the ones on the other side are dark. And you get that by basically the slopes facing towards the radar retro-reflecting energy more strongly than the back sides. So we knew they're ridges. We knew they're 20 to several hundreds of kilometers long. They're spaced by 3 or 4 kilometers. And if you model how surfaces scatter energy, we think they're maybe 100, 150 meters high, which actually makes them the spitting image of the largest dunes on Earth, the ones that we see in the Arabian Desert or the Namib Sand Sea in southwestern Africa. So this is a view from the space shuttle looking out across Namibia to the South Atlantic, and you see these ridges with just the same sort of arrangement as those we saw on Titan. So this discovery on Titan basically re-energized geological study of this type of dune, in fact. Some of us made a trip down to Namibia to study these dunes in more detail with a view to understanding what it is we're seeing on Titan. And you can see there's these nice flat interdune plains with the dunes in between them, actually relatively steep in between. And the materials are strongly segregated, right? The interdune material is of a different color from the sand. Part of that's vegetation, but some of it is sort of segregation of gravel from sand. And of course, you can use different methods to study how the history of the dunes. Here's some colleagues using a ground penetrating radar to try to resolve the structure of the dune, basically the different layers that get laid down seasonally. And you can have all the fun of geological field work of getting stuck and cooking sausages over a fire and all that stuff. And one thing that we've been able to do is start decoding what the shape of the dunes means in terms of the winds. If the wind blows in a constant direction, you get what are called transverse dunes that are basically orthogonal to the wind flow. But what we see on Titan is this linear form where basically the sand gets transported, on average along the dune. And that results from a bimodal wind regime where the winds are in a sort of converging, sort of chevron pattern. So that's helping us calibrate the weather models for Titan, because there are actually very few clouds to track to measure the winds. Like all solar system objects, Titan has been impacted. There are several dozen named impact structures. The largest was one we actually discovered on the third close Titan flyby in February of 2005. It's called Menerva, and is about 400 kilometers across. There's a sort of broad, shallow rim here. There's a river network flowing into it. Again, this is a radar image. These dark streaks, we didn't know what they were at first. There's more over here. These are, in fact, sand dunes now, we understand. And there's another river network outside. And actually, the character of this river network is suggestive of formation by very episodic rainfall, sudden changes in the amount of rain that's falling. But somehow this crater has been preserved since it was formed. I mean, we think it's billions of years old statistically. So not all craters get obliterated on Titan quickly. With one of the other modes of the radar, we can get some compositional indications, at least the dielectric constant of the material, which is different for organics than for ice. And it seems that what might be ice-rich material seems to be concentrated in the ejecta and rim of some craters. So that's suggesting that the impact event excavated this material and exposed it, whereas most of the surface seems to be draped in organic material, which is shown as darker colors in these near-infrared images. Most of Titan's craters actually are much shallower for a given size than craters on other bodies, the moon or even Earth, but certainly other icy moons like Ganymede, which is the same size, same gravity as Titan. So something is different about Titan, and we think it's largely that there's fluvial and aeolian, river and wind-blown sediment transport that's basically filling the craters in. So Titan, in many ways, is the most Earth-like of the icy moons or ocean worlds of the outer solar system. By the metric of on which planetary body would an unprotected human survive longest, Titan is also the most Earth-like. On Venus you'd get crushed and poisoned instantly. On Mars the air would get sucked out of your lungs and you'd pass out very quickly. But on Titan you could hold your breath for a few minutes, and then you'd eventually freeze to death. But it would take longer there than other worlds in the solar system. There are mountains on Titan. They seem to form belts, relatively short belts, 50 or 200 kilometers long. Maybe that somehow relates to the thickness of the crust. If this is some sort of surface to internal ocean faulting and tilt. We don't really know the structure. We just know that there are somewhat asymmetric and somewhat parallel mountains. There are a couple of kilometers in height. They're not insubstantial. They're mostly in Titan's equator. Maybe that says something about the global tectonic regime that generated them. Is it due to despinning of the moon, or perhaps tidal effects? We haven't really seen a convincing story of why they should be the way they are, but they are geographically distinct in where they occur. There are a few features that people have suggested may be what are called cryovolcanoes, volcanoes on an icy moon, where the lava is basically water, right? It's ice rock that's been melted, and so is water. And that's very interesting from an astrobiological standpoint, because if there are all these organics on Titan's surface, drizzling out of the atmosphere, formed by the haze, then the interaction of water with those materials, even for just a short time, can make a lot of very interesting prebiotic compounds. When you do this in the laboratory on Earth, you very quickly make amino acids, the building blocks of proteins. You can make pyrimidines, the bases that encode information in DNA. So, how far along the chain of chemical complexity that sort of interaction has gone, we don't know on Titan, but these cryovolcanic features, or putative cryovolcanic features, are probably the places of most interest. The most convincing example is Doom Mons, mountains, and named from mountains in the Tolkien books. And there's a bright area, Sotra Patera, that's adjacent to it, and actually has a deep pit. And the sort of juxtaposition of a deep pit with a mountain is something you see in volcanic areas. I mean, the Galapagos is a particularly good example. And there's something that looks like a flow coming out of this area that forms the broader Patera. And there's some other examples that look a bit like that. So, what does it mean if there's something that's flowed out of the ground? It actually doesn't mean it's a volcano. And the example I like to confront people with is maybe an unfamiliar one, is the salt glaciers in Iran, in the Zagros Mountains. Basically, there were layers of salt emplaced when this area was underwater in the Sea of Tethys, hundreds of millions of years ago. And superposition of sediments on top of the salt has warmed it and squeezed it, and in a few places the salt basically can erupt and flow out. I mean, it flows at like a meter a year or something like that before the very occasional rainfall dissolves these. The salt layers are, of course, what traps the organics in this area and makes it a very rich petrochemical reservoir. But this is stuff that basically is solid, and it's flowing, but it's flowing on a very, very long time scale, and it's coming out of the ground, but it's not a volcano. So could some of the features we see on Titan be something like this, that it's actually just organic sediments that have been buried and remobilized? And actually Arthur C. Clarke's science fiction novel about Titan, Imperial Earth, back before Voyager even sort of speculated that there might be something like this. He called them wax worms. So that, this just underscores that we have to be cautious in how we identify landforms and suggest how they might have formed. And in particular, we should be cautious about drawing conclusions about their composition. The rivers on Titan are generally not flowing. What we think we mostly see are river beds, like in desert areas on Earth. Those seen by the Huygens probe during its descent are, maybe this image is about 5 kilometers from the top here to the border of the highland here, but you can see the familiar branching network that's associated with rain-fed river channel networks. They exist on a much larger scale. This is in Xanadu, that bright leading edge area. Again, many orders of streams in the familiar, sort of branching network. So, the landforms are the same, even though this is liquid methane. Maybe it only rains once every decade or several, but it makes a familiar landscape. We see some features that might be alluvial fans, where a mountain river breaks out in a canyon into a broader plain and redistributes the material. This was actually seen on the first Titan flyby back in October 2004. And you can see in this radar image, this is again about 150 kilometers top to bottom, that the sediments are bright. The Cassini radar wavelength is about 2 centimeters, and basically the brightness means that the surface is rough on that 2 centimeter scale. But we actually found later on another example. Again, this is the southwestern edge of Xanadu, Tui Regio. Some examples of what look like river channels coming out from mountainous areas, and the radar brightness here, where you actually get into the electromagnetic modeling of how reflective things should be, if they are spheroidal particles of water ice. These are actually ridiculously bright. They're kind of like cat's eyes in the road, reflecting energy directly back at the observer. And the way you could get that is with basically radar transparent material, like ice is, relatively speaking, if the particles are a few centimeters across and are basically spheroidal. So here's a Jökulhlaup, sediment outflow associated with glacial outwash on Iceland, and you have this relatively uniformly sorted set of rounded cobbles, and it might be that basically if you make these out of ice and then take a radar image, what you see is on the lower left. So that raises the question, how hard is Titan material, right? If the rocks and cobbles are made of water ice or organics, how do they compare with familiar silicate rocks like basalt or quartz? And the basic answer is that things are 10 times weaker, hand wavy, but to a first order, that's what the laboratory measurements tell us. But the interesting symmetry is, of course, that the sunlight is weaker on Titan, so the winds aren't as strong. The gravity is weak, so things falling down like rivers do so less energetically. So we have less strong materials, but also less energetic processes moving them around. And those two effects seem to sort of cancel out and give us the same sort of landscape that we see on Earth, which I think is just a really charming sort of coincidence. You see sort of, badlands and mesas and other familiar features on Titan too. One of the most interesting features of Titan is its seas. So those dark areas towards the North Pole turn out to be seas of liquid methane. And in fact, I believe a version of this image is associated with the Geological Society's exhibition that Rose mentioned at the beginning. So these seas, this is about 1,000 kilometers from here to here. And we actually know how deep some parts of these seas are, because the liquid turns out to be fairly radar transparent, and we are actually able to ping with Cassini's radar the bottom. We got a bottom echo up here in this sea called Ligeia Mare, from a depth of about 160 meters. Which requires the liquid to be actually extraordinarily transparent. So this is very fresh liquid methane, basically fresh rainfall. It's been distilled out of the atmosphere. And that's kind of interesting, right? If you make some reasonable suppositions about how deep all this is and add it all up, then you have about between 100 and 1,000 times more liquid hydrocarbons in these seas than exist in all the known petrochemical reserves on Earth, which is kind of a fun statistic. There's no oxygen to burn any of it, of course, so it's pretty useless. But it's interesting to contemplate the wave generation processes in this liquid, the tidal currents, and you see very familiar coastal geomorphology, right? These sort of estuary branch networks. There's maybe some tectonically guided river channels here. There's islands we'll show in a second. There's again the same processes and the same resultant landforms, but from a very different working fluid. When we look at the seas and some of the coastal features up close, we see, for example, these islands here, Planktai Insulae, are the spitting image of some we see on Earth. These are at the top end of Oman in the Arabian Gulf. Basically, the Arabian plate is plunging underneath the Eurasian plate, and so these mountains are being progressively submerged, and that floods the valleys, right, and makes this very sort of dendritic and sort of craggy set of islands. And we see exactly that same thing on Titan, which suggests that either the sea level is rising or the land is sinking, or both. And actually, the reason we think all of Titan's seas are in the North Pole is that business of the asymmetric seasons, that because the southern summer right now is hotter than the northern summer, that's basically sweated out all of the methane moisture from the southern hemisphere and deposited it in the north. And that's something that reverses on timescales of roughly 50,000 years. So it's basically the same sort of Troll-Milankovitch cycles that drive our ice ages, and the formation of the polar layer terrain on Mars has the effect on Titan of shuffling the liquid from one pole to the other. And in the present epoch, we think the liquid is just accumulating in the north and flooding these valleys. There's other things going on. There's this looks like a valley that you can sort of see through some of the liquid. Basically, it's a valley in the seafloor. So presumably this was once exposed, hence allowing the river to excavate a channel. So there's again all the same things going on, but with a different working fluid and at different rates. The three seas on Titan, Punga, Ligeia, and Kraken, are named after sea monsters. Islands are named after islands in mythology, and inlets are named after inlets on Earth. And I have to claim some credit for suggesting Moray Sinus for this one, after the Moray Firth in Scotland, where I'm originally from. So I'll skip that. So we have a very diverse world, a lot of things going on interesting to explore just from the standpoint of geology, geomorphology, but also meteorology, oceanography. And then there's the whole organic chemistry thing. And that was really the question that we knew we would still have after Cassini. Cassini was not really equipped to tell us what the surface materials are made of. And that sort of set the stage for the next step in Titan exploration, which actually is the realization of an idea I proposed 20 years ago. When you look at the mathematics of flight in a low gravity environment in a dense atmosphere, helicopters are really a great way to do it. But 20 years ago, that was kind of a fantastical idea. And New Scientist had the most garish magazine cover on the article I wrote about this. But since then, there's been the drone revolution. We now know how to make autonomous rotorcraft, and it's a sort of logical next step to basically, if you have a lander on Titan, it's very easy to have it take off and fly a few kilometers and land somewhere else. Now, this doesn't look much like a regular helicopter. It's a quadcopter or octocopter layout. We have to have a dish on the top to send the data back to Earth. And we fold that down when we fly. Obviously, that's not something that's traditional in terrestrial aircraft, nor are drills. Right? You've got this really interesting engineering challenge of a helicopter wants to be light and to fly, and people who want to drill into hard surfaces want lots of weight on the drill bit. And sort of reconciling these sort of contraposed design drivers is a very interesting part of aerospace vehicle design. So Dragonfly, which is currently in development, is actually the size of the Mars rovers, and it's powered, we plan, by the same radioisotope generator power source. The rotor blades are actually about the same size as the blades on the little Mars helicopter that was dropped by the Perseverance rover, 1.2 meters across. So this is a development that's underway right now. Dragonfly will parachute down to near Titan surface, and then will drop out from the heat shield and land under its own rotor power, and will explore an area of the surface. And there's nice animations and a whole lot of other resources at our website, dragonfly.jsuapl.edu. So you can check out more details there, or use your favorite search engine. Where we're going is one of these impact structures, because we know from the Cassini data that there is a lot of water-bearing material that has been thrown out, probably impact melt. And that, as I mentioned, is probably the most interesting material from an astrobiological standpoint. And so that's what we want to go and drill and analyze with instruments on Dragonfly. Impact craters are not known for being particularly gentle places to land, so we'll actually aim for the sand dunes to the south, and then find a nice flat landing spot between the dunes, and then progressively fly towards the crater to explore the most interesting surface material. Dragonfly has been under development now for just about 2 years, most of which has been under the COVID era. It's been a challenge getting access to NASA wind tunnels, but we soldier on. We get the paperwork done and move ahead. One of the great things with a rotorcraft is you can test it on Earth much more easily than rocket powered vehicles. So we have a half scale test article. We have a big chamber at APL where we can basically cool it down to Titan temperatures and pump it up to Titan pressures, and check that the sampling systems and the rotor motors and everything work under Titan conditions. So there's lots of work underway. We've got a lot more work to do. We plan to launch in 2027, and we'll reach Titan basically one Titan year after Huygens descended, which is nice because we can use the Huygens information as ground truth about the winds and so on. So as I say, you can read more in books and on our website. Dragonfly will not be the end of the Titan story. Titan's an interesting place. Maybe people will go there someday. I think the next steps after Dragonfly might be to explore the seas, which are too far away for Dragonfly to reach, and to survey from orbit, to map Titan in more detail globally than Cassini was able to do. So a lot to think about and a lot to look forward to. So with that, I'll close and take questions.
Wow, thank you so much, Ralph. That was so interesting. Covered a lot of ground there, figuratively and literally, I guess. We've got loads and loads of questions come in. So I'll make a start. We'll get through as many as we can. People have been absolutely hooked all the way through. So let's start with this one about organic materials. So somebody has asked, when you're referring to organic materials, what do you mean? What are they specifically?
Right, so organic in this context just means carbon bearing. It does not imply a formation associated with living things in the sense that the word is sometimes used for soil. So what we probably mean in a chemically specific sense are short chain hydrocarbons, aromatics and aliphatics, probably polycyclic aromatic hydrocarbons like naphthalene, things with lots of basically benzene rings. Some of the material may be sort of tarry. Some of it is probably waxy. There may be basically analogs of evaporite minerals on Titan. Right, the liquid methane isn't a great solvent, but it can dissolve some amount of butane or acetonitrile, or pick your favorite compound out of the chemical catalog. And because we know there are these hydrological processes on Titan where the methane dries up, evaporates and gets rained down somewhere else. There are what look like dried lake beds on Titan, lake-shaped things that don't have liquid in them. And some of them have near infrared reflectivity that is quite different from the surrounds, that they're basically bright. Now, it's not bright with salt, the way sodium chloride or gypsum, the way evaporites are on Earth, but it's something else, whether it's butane or acetonitrile, we don't know. But those are organics too, but they are maybe not as optically dark as the sand. We don't know what the sand is. My guess is polycyclic aromatic hydrocarbons, but that's what is meant by organic in this sense.
Okay, great. Someone had actually asked if there was evidence for dried seabeds, perhaps in the southern hemisphere as well. So you've already answered another question too.
Definitely. Yeah. So let me just draw your attention to something on one of the maps. Yeah. So there is this thing in the south. This is called Ontario Lacus. Lakes on Titan get named after lakes on Earth, which is going to get confusing sooner or later, I think. So it's 200 kilometers by 70 kilometers across. And it actually, maybe you can even see it, it actually has this optically bright margin to it. And the shape of this lake is very similar to playas in the desert southwest of the USA. Racetrack playa, actually, where the rocks move around, is a good example. So that's consistent with this lake, which is in a very shallowly sloped area, with this lake shrinking. And actually, from the Cassini radar information, we think that Ontario Lacus is more ethane rich than the seas in the north. Now, ethane is less volatile than methane. It's a liquid at Titan temperatures, but in a way, it's almost like salt in the Earth's oceans. So maybe because the south is drying up and this residual lake is shrinking and shrinking, it's becoming more ethane rich, whereas the methane is getting distilled over to the north. So we're sort of seeing this migration of volatiles in action on Titan.
I see. Okay, kind of answered it 2 in 1 there. That's great. We've got a few questions coming in about Dragonfly Mission. So someone is asking what's the intended mission length for it, and also how's the drone going to be powered?
Yeah, so the planned mission duration is a little over 3 Earth years. We expect during that, basically we expect to make one flight every couple of Titan days. and a flight is only half an hour long, but basically uses up half the energy in a big battery, and we will recharge that battery with the radioisotope generator, just like the one on Perseverance. I mean, it puts out 80 or 100 watts, which is not enough to fly. I mean, it's only enough to run a couple of light bulbs, right? But most of the time, especially during the night on Titan, 8 Earth days long, we're just sitting there. I mean, we'll take seismic data, we'll record the weather, but most of the nighttime, we're just recharging that big battery. And as I say, we'll maybe make a flight once every 2 Titan days or once a month. Each flight probably takes us 5 kilometers or so. So over the 3 years, we should be able to get from the landing zone in the dunes, towards the crater. There's nothing, hard and fast happening after 3 years. The isotope generator will, slowly reduce its power output. So we'll have to maybe space the flights out longer to allow longer to recharge. But you kind of have to design a mission with a cutoff so that the budget people have a horizon to plan to. Often missions get extended. We might hope that would happen, but obviously there's a lot to happen between now and then.
Of course, and as you said, there's further missions planned after Dragonfly as well. So
certainly hope for, let's say.
Hope for. Okay. We've got a few questions coming in about geomorphology as well. Various topics we're looking at, but let's start with, Sally is asking, can there be any caves or underground features, underground rivers on Titan? Does the Titanian geology favor caves or karst in general?
That's a great question. In fact, there was a what turned out to be wrong laboratory measurement in the 1980s that suggested that liquid methane might dissolve ice quite well. And there was even a very popular artist's impression of karst terrain, with this sort of nice arch. And then some rotter discovered that actually the measurement was wrong, and ice doesn't dissolve very well in methane. So you can look at some features. Let me try and remember where we are. Yeah. So how much of this etching of the terrain is due to mechanical erosion of cobbles being tumbled in a stream and mechanically abrading the bedrock versus dissolving it, we just don't know. The fact that there is a lot of this, and many of the I didn't talk about the lakes, I only talked about the seas, but there are lots of, actually off the top of this figure, there are lots of little lakes and many lake-shaped depressions that are empty, and they look a lot like karst lakes. We don't know that that's how they formed. We just don't know how they formed, in fact. It is also the case that the sea level is basically the same everywhere, which might imply there's a lot of hydraulic connection between the different seas and possibly some of the lakes. But that's that depends on how much rain is falling as a function of latitude. So we certainly can't rule karst out. There are some circumstantial indications for it, but we really don't know.
Great. Gosh, that's so interesting. There's like so much to explore still, isn't there? You mentioned the seas there. Actually, lots of people are asking about tides as well. Are there, do the mare on Titan have tides at all?
Absolutely. This is one of the fun things that I didn't have time to put in the talk. There's some material in the book. So if Titan had a global ocean, and actually at one time we thought it might, then Saturn's gravity basically makes a 100-meter high bulge. And on the Earth, the moon's gravity, at least where the moon is today, it was closer, in the past, makes a bulge that's about 20 centimeters high. But because Titan is synchronously rotating, Titan's solid body is fixed with respect to the tidal bulge. So the bulge would be there, but it wouldn't change, except that Titan's orbit around Saturn isn't quite circular. And because Titan gets a little bit closer and a little bit further away, that bulge would go up and down by 100 meters. But there isn't a global ocean. There are just the seas that you see that cover about 1% of Titan's surface. But when you look at the models in detail, you find that the tide between tidal range between, say, here and here across Kraken is about 0.5 meter. And it actually depends how squishy Titan's interior is. And we know it's a little bit squishy from Cassini measurements. Because the tidal period is so long, 16 days, there aren't resonant tides, right? You don't have situations like the Bay of Fundy, where a sort of natural Seiche oscillation is at the same period as the tidal forcing period, and you get this resonant buildup of bigger tides. That doesn't happen on Titan, unfortunately. But we think there is a tidal range of about something like 0.5 meter here, and there's probably some tidal mixing through the channel here, certainly through this channel here, which is about the size of the Straits of Gibraltar. We think there's more rain towards the pole, and that may have the effect basically of flushing out the solutes like ethane. So Ligeia we know is pretty methane rich, ethane poor. Kraken may be more ethane rich. So this may be like the Baltic and the Atlantic, or the Black Sea and the Mediterranean, that the runoff from the land, which is basically fresh, pure methane, is flushing out the salts, flushing out the solutes into the more equatorward seas. And how effective that process is depends on how much tidal flow there is back and forth. So yeah, there's a whole field of extraterrestrial oceanography that is just kicking off.
Mm-hmm. And with you mentioning the the rain there on the highlands, someone's asked what actually drives the rain on Titan.
Right, so it's the same thing as on Earth, that there's the sunlight causes evaporation. We saw cloud activity over Titan's south pole when Cassini arrived, and we'd actually seen it with ground-based telescopes before Cassini arrived. So that was during southern summer. Basically, the solar heating is driving moisture out of the ground and causing convection, and the convection causes rainfall. Then that all stopped actually very soon after Cassini arrived, which is slightly frustrating, although good in terms of seeing through the clouds and seeing the ground underneath. Then during the equinox around 2009, we saw cloud activity at the equator. Right, and that's where the sun was, right? So the sun was basically driving updrafts, convection that then formed clouds and rain over the low latitudes, and actually those storms we think are quite important in shaping the winds to cause the dune arrangements that we see. And then towards the end of Cassini's mission, when it was northern summer, we started to see clouds picking up in the north. They actually picked up rather slower than many of the models expected. So that's the great triumph of science, right? When the model's wrong, then nature is telling you something that isn't in the model yet. So we still need to tune the knobs to try and understand how the hydrological cycle works on Titan. But basically, it's solar driven.
Okay, so we just had a question come in that says, why does Titan have such a significant atmosphere, unlike other satellites of Saturn?
Yeah, that's the big question in a way that Cassini was in part posed to answer. So we have part of the answer. There was the idea that that Titan might have a dense nitrogen atmosphere because nitrogen could get trapped in clathrates, in very cold ice. But if that was the way that the nitrogen came to Titan, then we would find a lot of argon-36, an isotope of a noble gas, which is a good tracer. And Cassini measurements showed there was hardly any argon-36 there. There's argon-40 made by radioactive decay, but that's unrelated. So Titan cheated somehow. It was able to get nitrogen which is kind of too volatile for where Titan is in the solar system. There's nitrogen on Triton at Neptune, 3 times further from the sun, but not in the Saturnian system. So what we think happened was that the Titan cheated by having ammonia, which is much less volatile than molecular nitrogen, come in as hydrate, and there was basically a primordial atmosphere of ammonia that was converted by lightning or shock from impacts or something into the nitrogen we see today. But it sort of cheated is the quick answer.
Okay, I like that. Let's go back to some more geology-based questions. I'm rattling through these because they're coming in thick and fast. So
that's great.
Let's have a look at some geology questions. So John has asked, have any landslides been observed on Titan? How frequently do they happen?
No, and in fact, there's very little in the way of geologic change that we've seen on Titan because the processes are one, relatively slow. When we saw what might have been a lake level drop in Ontario Lacus down here in the south over several years. But the simple fact is that the data we have for Titan is just not good enough to detect change, right? If you wait for millions of years, then volcanoes erupt and islands disappear, and lots of stuff happens. And at the large scale, you can see that. When you only have a few years, you can't see big things happen because they just don't. The reason we've been able to see changes on Mars, like landslides and even dune migration, is because we have cameras in orbit at Mars that can see things this big. Right, the high-rise imager on Mars Reconnaissance Orbiter has a resolution of a half or a third of a meter, and for many years it was actually a puzzle. Why aren't Martian dunes moving? Because the winds should be strong enough to move sand around, and it was only because we had several year baselines to record change at meter length scales that we could detect those events, and that includes some landslides. Cassini, with at best 300 meter resolution, just doesn't have the capability to see a lot of change. There have been maybe some patches of brightness changes, basically sand moving around or dust deposition, that sort of thing, but there's no reason to think landslides don't happen on Titan, but we just don't have the data to support it yet.
Yeah, of course. And actually someone's asked if any bedded outcrops have been observed from orbit, but presumably it's the same issue with the kind of data resolution there.
Yeah, so I mean, we see, just even looking at this image, that sedimentary processes are likely to have been extremely important in Titan's history, with the seas drying up and depositing, and rivers flowing and sand blowing around. But the best sort of image to see that sort of thing would be this sort of oblique view that we kind of have from Huygens, but this is several meters resolution at the surface. So Dragonfly may be quite well posed to record that sort of layering, or on some future mission, perhaps, if we have a ground penetrating radar, and those have been advanced. In fact, this long antenna here was intended to represent a ground penetrating radar like Marsis or Charade on some of the Mars missions. So that would be something definitely to try.
Okay. Another geology-based question I've got here: how high are the mountains on Titan? Are they high compared to our mountains?
The short answer is they're generally smaller. I mean, the topographic range, as I mentioned in the early part of the talk with the hypsogram, the entire range from highest mountain to deepest pit is about 2.5 kilometers, something like that. The highest individual mountain, which has such a small area that you can't really see it on that picture, is what, 3 and a bit kilometers high. We did actually have a bit of a debate early in Cassini as to whether you can actually call these mountains, right? If this is 500 meters high, does that make it a mountain? If it's 501, is it a mountain then? there's actually no accepted criterion we could find for what's a mountain versus what's a hill. Everything's sort of relative, right? Titan's a smaller body, so if there's a terrestrial standard, do you multiply it by 2575 divided by 6370? So there are a few mountains that are 3 and a bit kilometers high is the quick answer, but generally Titan is pretty flat.
Okay. I'm gonna switch back to some Dragonfly questions now, because people are still asking lots of questions about that mission. So someone said, is there a possibility that mission creep could happen with Dragonfly, in that it could carry a probe to sample a mare, much like how Ingenuity hitched a ride with Perseverance?
The short answer is no. So Titan's radius is 2575 kilometers. So 60 degrees of latitude is 2,500 kilometers. So here's where Dragonfly is going, and this Dragonfly was proposed in response to a call for proposals that laid out specific mission goals, and the mission goals for Titan were astrobiological. What evidence of prebiotic chemistry is there? What habitable environments are there? So the habitable environment stuff is the deep ocean, which we explore with seismic methods, and the surface chemistry is what we address. The surface chemistry of water-bearing impact deposits specifically is how we address the astrobiological goals. So the proposal call didn't ask for a mission to explore Titan seas. There is the point that, as was the case when Huygens arrived, the mid-2030s, when Dragonfly will arrive, is southern summer, right? The sun is down here. So the northern seas are in darkness. Not only are they in darkness, but they're not in geometric view of the Earth. So we can't radio data back to Earth. So even if we could reach the seas and Dragonfly is going to fly maybe a couple of 100 kilometers, from here to here. 2,000, 3,000, 4,000 kilometers is beyond its range. But we also wouldn't be able to get the data back because the Earth is below the horizon. So no, we are not going to be able to do that. That's something for a future mission. There's no reason a Dragonfly-like vehicle wouldn't be the right platform for such a future mission, but it would need to wait till the 2040s for the Earth to be visible, unless you have a relay orbiter, which is another $1 billion.
Wow. Okay. Actually, the person who asked that question has just responded to say that's fascinating. Thank you. Okay, a couple more before we need to wrap up. Someone has asked, can you get tornadoes or even rainbows on Titan?
Interesting. Tornadoes I hadn't thought about. So tornadoes are driven by moist convection, and methane we know forms does form storm clouds on Titan. That's what makes the rivers. We even saw with Cassini actually about around about this area here in the equinox season. There were clouds that appeared, and then some of this terrain actually got darker for several months, and then got brighter again. And we think basically it was darker because it was wet. So there are storms. No reason those couldn't have rotating elements like tornadoes. We've no evidence of them. But rainbows would also be a possibility, right? Rainbows result from the reflection and differential refraction within drops. And there's when you look at the physics, the refractive index, the refraction properties of liquid methane are a little different from those of water. The refractive index is less, and that has the effect of making the rainbow wider. The rainbow would actually be a little bit bigger than rainbows on Earth, but it would be less pretty because the haze in Titan's atmosphere is made this sort of reddish organic stuff that basically blocks blue light. All the blue light's absorbed high in the atmosphere by the haze. A little bit of green filters down, but most of the light that gets down to the surface on Titan is red and near infrared. So yes, there could be rainbows, they'd be a bit bigger, but they'd just be kind of a sort of bright red band. If you could look with in the near infrared, you'd actually see dark bands in the rainbow, because methane absorbs light at specific wavelengths, which was actually how we discovered the atmosphere on Titan. So there could well be rainbows. We didn't see any because Huygens landed at the equator during southern summer, which is the same reason that we aren't worried about rainstorms or tornadoes or anything for Dragonfly, because if there is any energetic convective activity, it's down here at the South Pole when Dragonfly is up at the equator. So that's a pity. It means we're not likely to see any rainbows, but can't have everything.
Yeah, again, maybe on a future mission we'll get to see
Right.
those. I'm just looking at the time, and I think we are going to have to call it a day there. I think we got through most of the questions though, so that's great, and thank you for staying on to answer all of those. And thank you for such a fantastic lecture. That was really, really fascinating. So it's great to have you with us. To everyone watching, all our lectures are available on YouTube after they're streamed live, so keep an eye on our YouTube page and we'll add it to the Aerospace playlist if you want to take a look at this again or look at any of the others we've had in the series this year. Our next scheduled lecture is the Geology of Pluto on the 10th of November. We are hoping to squeeze another one in between now and then, so keep an eye on our social media or our newsletters for updates. But yeah, thank you everyone for attending. Hopefully we'll see you next time. And again, Ralph, thank you very, very much. And
my pleasure.
Yeah,
Thanks all.
take care. Thank you, everyone.